In the first lecture, you encountered the wave equation, and that told you about waves going in one particular direction or in the opposite direction. So f of x minus vt will give you waves that way. With v reversed, the wave will be going the other way. But the waves can somehow combine with each other to make other kinds of waves called standing waves, which go nowhere. But actually, they're everywhere. So when you play a musical instrument, so for example, a guitar, you pluck the string of a guitar, you've given energy to that string, the string vibrates, and it sets up a standing wave inside that instrument. The same goes for drums, the same goes for other musical instruments. And standing waves have applications in a lot of places. So today we're going to take that wave equation and see how to solve it. And in doing so, we learn about the use of what are called basis functions. So the point of that is that you can write the solution as a sum of basis functions. And so all you have to do is to determine the coefficients, and that will, what the boundary conditions will determine. Let me begin by reminding you of what we had discussed the last time. So here is the wave equation. It's a partial differential equation, d2 dx squared minus 1 over v squared d2 dt squared. And if f is a solution, well then it's got to be a function of x and t, of course. Well then that's what the solution means, that this operator over here, the second derivative with respect to position, second derivative with respect to time on f is 0. And remember, the dimensions are good here because velocity into time is distance, and so that's fine. Now, any solution has to have the form x minus vt. And I showed that by simply substituting this in here. And if you recall how we took partial derivatives, well, that's the solution. But what about a different solution? What about some other function, let's call it g, which is not a function of x minus vt, but which is a function of x plus vt? Well, the only difference is that this wave was going this way. So x equal to vt is where the peak of this is located. But this wave is going the other way. So it will be going this way with negative velocity. Okay, now here comes the principle of superposition. Superposition simply means that I can take two solutions and add them together. So the principle of superposition says that f of x minus vt and added to that x plus vt is also a solution. Well, how do you check that? So why? Well, it's actually pretty trivial. When you put just this in here, you got 0 on the right side. If you put this, just this in here, you'll also get 0. And so this plus this is a solution. So in general, so this is a very, very important fact. A sum of solutions is also a solution. A solution of the wave equation. And in fact, it's more general than that, but okay, so to just repeat, this first function is going this way, this second one is going this way. And now what I want to talk about is how, in general, does one know what the solution is? One knows the solution of the wave equation. And now, this by itself is not going to tell you everything. You have to know what the boundary conditions are. So let's go back to that animation which you saw earlier. Okay, so here is a string, and I'm going to use the manual mode this time. I'm going to give this a jerk. And you see that a pulse is propagating, and it's propagating and it's gone through the window, and it'll keep going forever and ever. Now, that's a boundary condition which says that there's no condition on the right-hand side. So the pulse will keep going. The boundary condition that I had applied over here was that it went up and down. And you see, whatever I do over here will now keep going to the right. Okay, now I'm going to change my boundary condition. Now I'm going to fix this. I'm going to fix this end over here. And now let's see what happens when I give this a jerk. So the pulse is going to the right. It goes, meets the end, and then is reflected back. And it's coming back, and then it is reflected again, and it'll keep on doing this forever and ever. Because there is, as you can see over here, no damping. Okay, now let me stop this here. I will give this a pulse, and you see this pulse is going to the right. And as it's coming back, I'll give another pulse. And you see that both of these go independently of each other. So this is what is called the principle of superposition. You can just add the solutions to one another. Okay, now let me stop this here. And instead of just giving pulses over here, I'll ask it to oscillate. And now with the oscillations, I can choose the amplitude, I can choose the frequency, I can do these other things over here. Let me give it some frequency in the middle, let's say something like 0.6 hertz. So, okay, so this goes up, comes down, and now you see that this wave is propagating to the right. It's being reflected from there, and it's coming back. So this is a periodic source. The amplitude over here is changing periodically. And so there's a boundary condition over here at this end, and there's a boundary condition at this end, and you see how big a difference the boundary condition makes. So in other words, until you know the boundary condition for the wave equation, there's no question of your being able to solve it. Instead of pulses, let's now consider periodic waves. In other words, those waves which repeat themselves. So for example, let's take this f of xt, which is, I could have put an amplitude over there, but I'm too lazy to do that. And there's unnecessary writing there. So let me just take sine of kx minus omega t, which you can always write as sine of, well, k of x minus omega over k t. And now recall what we had discussed the last time, that omega over k is what we call v. V is the phase velocity. And so what we've done is we've taken this periodic function sine of kx minus omega t and put it in the form x minus vt. And so obviously you know that this is going to be a solution of the wave equation. Okay, but why not verify it? It might be just good practice. And also, you remember over here that when I called omega over k as v, I had said that k is what we call the wave number, and it's essentially 1 over the wavelength lambda. All right, now let's verify that f is the solution of the wave equation. So for that, what I need to do is I need to take df by dt first. Okay, if I do that, then when I differentiate over here, well, by the way, let me do a little simplification here. I can write this as sine of, instead of k, I'm going to write 2 pi over lambda, same thing. I could have done without this, but that's okay. So x minus, let's call this vt. Okay, so now I want to verify that this f is a solution of the wave equation, for which I need df by dt, and that's obviously equal to minus 2 pi v over lambda times, so when I differentiate sine, I get cosine of 2 pi over lambda x minus vt. And then if I differentiate this again, so I have d2f by dt squared, well, I'm going to get second 2 pi over lambda v again over here, again with a minus sign, but when I differentiate the cosine, I get a negative sign. So from there, I get minus 2 pi v over lambda squared, and I get sine of what I had before as well, x minus vt. Okay, very good. Now, if I do the same thing with x, so df by dx, so I'm going to differentiate this with respect to x. In that case, I'll get a k cosine, and well, of course, or if I differentiate this, I'll get 2 pi over lambda and cosine of all this stuff inside. Why rewrite it again? And then if I differentiate it one more time, so d2f dx squared, well, when you differentiate cosine, you get a minus sign, so the only thing is that I will have over here minus 2 pi over lambda squared cosine, sine of all that stuff which was there before. Okay, so that's the second derivative of f. That's the second derivative of f, but with respect to t. And so let's add them together, and you see that d2f dx squared minus 1 over v squared d2 dt squared, when it acts upon this f, is going to give you from the first part, from here, it's going to give you minus 2 pi over lambda squared times sine, and from the other, because there's this additional minus sign, so it's going to give you plus 2 pi over lambda squared sine, and the same thing there. So this adds up to 0. Okay, you see the v over here was essential because there's a v squared here, and when we differentiated there was a v squared here, so I get 0 over here, and that's exactly what you want. Okay, now from here we see that this is a solution, and remember that, and this is very important for you to remember, that we'd found that omega was k times v. That's one very important thing to remember. And the other, which follows immediately from this, if you put k equal to 2 pi over lambda, then from this is that lambda into the frequency is equal to v. These two are saying exactly the same thing. K is equal to 2 pi over lambda, and omega is equal to 2 pi times the frequency. Let me write that over here. This omega is 2 pi times the frequency, and k is 2 pi over lambda. Always remember that. Okay, so to conclude this point, this function satisfies the wave equation. We check that explicitly. If you had over here plus omega t instead of minus omega t, it would also have satisfied the wave equation. No difference whatsoever, because when you take second derivatives, then the negative signs cancel out. Now at this point, since we're dealing with trigonometric functions, I need to remind you a little bit about trigonometry. So let's do a bit of trigonometry. And here, I remind you of something that you, certainly learned in school, but need to refresh. That if I have the sine of a difference of two angles, A minus B, that's sine A cosine B minus sine B cosine A. And one way I always check is that suppose A is equal to B, the left side is 0, is the right side 0? It is, and so that's one of many, many checks. All right, but what are we really interested in? That's sine of kx minus omega t. What I'd written before and showed you was the solution of the wave equation. Let's apply this formula here. So this is sine kx cosine of minus omega, cosine of omega t, so that's, and there's minus sine of, now it'll be sine of omega t and cosine of kx. If I had this sine of kx plus omega t, and you remember that this is the wave that's going in the backward direction, what would be the difference? I would have sine kx cosine omega t, and here, because omega has gone to minus omega, so this sine over here would change, and I'd have sine of omega t cosine of kx. All right, so now I'm saying that this is a solution and this is a solution, and so their sum is a solution, which means that I have two other possible solutions. And one I get by adding them, one I get by subtracting them. So if I add them, I will get the first one. If I subtract them, I'll get the second one. And so I have sine of kx, cosine of omega t. That's a solution. But also this is a solution. Cosine of kx, sine of omega t is a solution also. All right, now I'm sure that you must be very confused because look, I said this is a solution and that is a solution and this is a solution and that is a solution. Well, we call this one basis and we call this another basis, and they're both the same. You see, you can write this as a combination of this and this, or you can write this as a different combination of this and this. So this set over here is equally good as this. Of course, they have different physical meanings. This is a wave going to the right, this is a wave going to the left. This is actually a sum of these two, and this is a difference of these two. So now, boundary conditions will decide upon the actual solution. So as I said before, boundary conditions are absolutely essential. Without them, you can't tell what the solution will be. We're now going to be looking at the boundary condition which leads to what are called standing waves. So look at this point over here. At this point, no motion is possible. In other words, the function has to be 0 here. Similarly, it will have to be 0 here as well. Now, what I'm going to do is have this animation throw waves which will travel from this side to this side over here, then be reflected, and then they'll go back here and again be reflected, and we'll see what happens as a result of that. Okay, so in the beginning, I'm just going to show the incident wave. Let's start from here. Okay, so a wave somehow comes and it's been created maybe by shaking the left-hand end, and it's moving towards the right. It's moving at a speed which is, of course, the speed of the wave in that medium, and we can, if it's a string, we can adjust that speed by changing the tension. That's what we'll come to later. Okay, now, so this is the incident wave. I'm going to stop this and show you the reflected wave. Well, maybe I can show both of these. So the incident wave is coming in and the reflected wave is going back. Now this will get a little confusing, so I'm going to now shut off the reflected and the incident wave and just show you the resulting wave that forms from the incident and the reflected waves. So you see, before we go to the mathematics, just have this in mind, that this point over here is fixed, this point over here is fixed, so the function has to be 0 here as well as here. And now we shall use the basis that we just discovered for the wave equation to proceed. Let's now understand standing waves mathematically. And we shall do so using the solutions of the wave equation that we found, one of which was sine kx cosine of omega t, and the other was cosine of kx sine of omega t. You could have directly put this or this into the wave equation, and you would have seen that this would be a solution. Now, by the principle of superposition, the actual solution can be a linear combination, or just, that's a fancy word for saying just the sum of this and this with different constants in front. So let me take A to be one unknown constant. It's unknown, but we'll soon find it out. Plus B, which is another unknown constant, also to be shortly discovered. So this is a solution of the wave equation, but now we have to make the solution obey the boundary conditions. What are the boundary conditions? Well, that on the left side, that is to say at x equal to 0, for all times, the string is held fixed. So f is 0. There's no motion, there's no transverse motion at x equal to 0. Similarly, on the right side, that is to say at x equal to L, at any time, for all times, there is also no motion. So the right hand is fixed and the left hand is fixed, which means that this now has to obey these two conditions. So let's take the first condition. So f has to be 0. This has to equal to a sine of k into 0, cosine omega t, plus b, and now at x equal to 0, we're going to have cosine of 0 sine omega t. And now, as everyone knows, sine of 0 is 0, cosine of 0 is 1, which means that b simply has to equal to 0. So that was the first boundary condition. Let's use the second boundary condition, which says that 0 must be equal to, now here I have to put x equal to L. So I have a sine of kl cosine of omega t. That has to be 0, and it has to be 0 for all times. So, well, we have only one option, which is that a is 0, but if a is 0, then this entire solution is 0, now that we found that b is 0, and this would be, yes, it would be a solution, but it would be a trivial solution. It would be a very uninteresting solution. So we'll exclude a equal to 0. Cosine of omega t is not 0 for all times, and so that puts the condition that sine of kl must be equal to 0. Now you know that the sine function looks like this. It starts from 0, goes up, comes down, goes up, comes down. And so we must have that kl must be equal to either pi or 2 pi or 3 pi, etc. In other words, there are different values of k possible, and so kn into L must be equal to n times pi, where n is 1, 2, 3, etc. And we exclude n equal to 0 because then the sign is 0 and it's uninteresting. Okay, which means that we now have a solution which is that f of xt is some amplitude a times sine of kn, which is n pi over L, times x. And of course, there's the cosine of omega t. But you remember that omega is equal to v times k. And so since only particular values of k are allowed, k1, k2, etc., therefore only particular values of omega are allowed, and so that must be reflected here. So this over here is the standing wave. Now, if I put n equal to 1, then so it becomes this, n pi over Lx. When I put x equal to 0, this vanishes. When I put x equal to L, then this is sine of n pi, which also vanishes. So this satisfies this boundary condition and that boundary condition. And that, well, is the solution. Now, of course, when we plot this out, what this gives us is the following. So here is x equal to 0, here is x equal to L, and the solution with n equal to 1 will look like this. Then when I put, so when x is, you see that when x is equal to pi by, when x is equal to L over 2, that is to say over here, then this is sine of pi by 2, which is 1, which is the maximum value, and so it goes to its maximum in the middle over here. This is called the fundamental mode. And then if I put n equal to 2, well then it will be 0 over here, and so it will look like this. And I've put n equal to 3, then it'll be more complicated. It'll have this point over here is called a node. Then it'll have 2 nodes, and then 3 nodes, and 4 nodes, and so forth. But this over here now is the solution, which is called a standing wave. Why is it called standing? Because suppose you're at one place. You are, let's say, at the middle over here. Then what you will see is that, for example, here, the function or the displacement will always be 0 if you are in if it is the second mode. If it is the first mode, then this will be going up and down, up and down. There's no motion to the side, this way or this way. That's why this is called a standing mode. And basically, as you saw in the animation, it comes about because you have a wave that's going this way, and you have a reflected wave that's going this way. When the two meet with each other, sometimes they add up, sometimes they cancel, and that leads to a standing pattern. That's the standing wave. Before we end, I'm going to give you one more basis set of functions. Okay, so just to remind you, for the string that we have looked at, we said that sine kx minus omega t or sine of kx plus omega t, this is a good basis set. You can expand, you can take a linear combination of these, or we could have taken sine of kx cosine omega t and cosine of kx sine omega t by taking a different, by taking this plus this or this minus this, we would get this. Now, it's sometimes good to look at this thing, e to the I kx minus omega t. Now this is very convenient when we deal with the wave equation. This is the exponential, this is iota, and it is actually quite obvious that this is a solution of the wave equation. Let's check that. So if f of xt is this, then this is obviously of the same form as this, and so you expect it to be a solution. But let's quickly work this out. So if I take d by dx of f, well, this is going to give me I times e to the I times the same thing over here, kx minus omega t here. If I take a second derivative, d2f, if I take d by dx of f, I get ik times this. If I take the second derivative, d2f dx squared, well, I will get ik and then ik again, so ik squared e to the I this, which is of course minus k squared e to the I, let me write it out now, kx minus omega t. Fine. And so d2f dx squared we have computed. Let's take d by dt. So d by dt of f. Well, in that case, the only difference is that I would have, look over here, instead of ik, I would have minus I omega. So I had minus I omega, and then it would be e to the I. And then if I take one more derivative, d2f dt squared, well, it'll just be minus I omega squared e to the I this. And this, of course, is again just minus omega squared e to the I kx minus omega t. All right? It's obvious from here that d2f by dx squared minus 1 over v squared d2f by dt squared, that this is equal to, so from the first one I have minus k squared e to the I kx minus, and from the second I have omega squared over v squared e to the I kx minus omega t. Now, this has to equal to 0, which is only possible if this factor over here is 0, which means that I must have omega squared is v squared k squared. And that's exactly what we had before. You remember that omega is equal to vk from our earlier discussion. And so, of course, this is a solution. This is a solution of the wave equation. We've seen that explicitly. Now, here there are two possibilities. Omega could have been plus omega could have been positive, or omega could have been negative, which means that not only is this a solution, but also when omega, if instead of omega you have minus omega, that too is a solution. So, in fact, the two basis functions will be e to the I k x minus omega t and e to the I kx plus omega t. And these two functions are going to be very important in understanding details about the wave equation and for Fourier analysis, which we will come to at a later point.